Welcome to Unit 2. In our last unit, we talked about electron configurations. We talked about valence electrons. In this unit, we're going to kind of expand on that a little bit more. We're going to use the periodic table a little bit more with this discussion. And as we do so, we will be able to look at some of the different patterns that appear on the periodic table. And that's one of the things that we're going to start by talking about is instead of patterns, they use the word trends. A periodic trend is just a pattern that we're going to follow on the periodic table. So previously, for example, we learned that if we look at a periodic table, we learned about valence electrons. And we said every element in this first column here has one valence electron, and then here they have two. And remember, valence electrons are those ones that are in the very last shell. And then remember, we skipped the D subshell because those are one behind. And then it went 3, 4, 5, 6, 7, and then the noble gases have 8. Okay? So one of the very first periodic trends that we'll see here is that here, for example, we're talking about chlorine. Okay, chlorine is right over here. It's right underneath fluorine in that in the column that has 7 valence electrons. And a lot of times in chemical reactions, especially with medicines and drugs and things like that, they think, okay, what if we take one of these atoms out and replace it with a different atom? How will that affect, something like that can make a big difference. You drink water that's H2O. Well, if you add one more oxygen to water, you get hydrogen peroxide, which you do not want to drink. So a lot of times one little atom can make a big difference in how our bodies, or how a paint color, or how the strength of the steel can change depending on that one extra element that you replace. So if we were to replace chlorine with a different element, we're trying to find another element that would react similarly to chlorine, because of course chlorine is right here. So what's another element that we might also expect to behave chemically similar to chlorine is another element that's in the same column because it has the same number of valence electrons. Okay, and that's what that last sentence says right there. That's the important one right there. It's that atoms with the same number of valence electrons tend to react in similar ways. So if you're going to replace an atom in a chemical reaction and you want it to react similarly, well, then you would replace it with an atom that is going to have the same number of valence electrons. Okay? Now, another one. So trend number one is atoms that are in the same vertical column have the same number of valence electrons and react in similar ways. So therefore, you can replace one for another and know that their chemical reactivity is going to be somewhat similar. Okay, the second one is called ionization energy. Okay, a couple of big words there. Ionization is when something ionizes. Well, what's something that ionizes? It's when something gains or loses electrons. Remember an ion. So an ion is something that is an atom that has gained or lost electrons. So ionization is just that same process of an ion forming when an atom gains or loses electrons. Okay, so atoms can gain or lose electrons and they create ions. Okay, but what that does is it takes energy to do that, especially when you take an electron away from an atom. Okay, that always requires energy. And why is that? Well, because the electrons are attracted to the nucleus. The electrons with their negative charge way out here, and here's the nucleus way in here with its positive charge because of all the protons. There's an attraction there. Okay, opposites attract. Okay, we know that. Okay, just like a magnet. Okay, a positive and a negative are attracted to each other. Same thing with an atom. So it takes energy to remove an electron from an atom, and that's exactly what ionization energy is. Ionization energy is the amount of energy that's required to remove an electron from an atom. Okay, so here you can see that. Here you can see a chemical formula written for this. So magnesium, a regular magnesium atom, is going to lose an electron, and now notice it has that positive charge up in the corner. Okay, and so we can actually write like a chemical formula that shows this is regular magnesium, and now here's magnesium after it's lost an electron. Here's that one electron it lost, and this right here, this triangle looking thing represents is the Greek letter delta, like Delta Airlines has a bunch of triangles on their airplanes. Okay, delta means the change in. Okay, and so this represents this whole thing here together, the delta E, that whole thing means the change in the energy. Okay, and so that means it takes 738, and don't worry about the units, those are called kilojoules per mole. Don't worry about what those mean yet. Okay, but it takes some energy in order to remove that electron from the magnesium atom. And then now magnesium can lose another electron as well. So you start with magnesium already having lost one with its positive charge, and now it's going to lose another one to become Mg2 plus, and now again it's lost that next electron. And notice the change in the energy. Notice it goes up by quite a bit. Okay, well, what does that mean? It means it takes more energy to remove the second electron than it did the first. And let's think about why that would happen. Here, let's say this is magnesium. So we've got our 12 protons in the nucleus, and we've got 1s2, 2s2, 2p6, and then this would be 3s1 and then 3s2 way out here. So right now you've got these, this is a valence electron, that's a valence electron, and then here's all the inner shell electrons. So I take this electron away. So now it took some energy, and that electron is now gone. Well, now there's still the same number of protons here, but now there's only 11 electrons to attract instead of 12. And so every time you take an electron away, the electrons that are left feel a little bit stronger attraction to the nucleus because there's now less electrons to attract. So every time you take one away, you're going to see this increase in ionization energy, and that's going to cause it to require more energy to take the next one away. So as you remove electrons from an atom, the remaining electrons get closer to the nucleus and are more attracted to the nucleus because, again, the protons haven't changed at all. There's now just less. Why are they more attracted? Because there's less electrons to attract. And as you take more and more electrons away, the more attracted those remaining electrons become, and the more energy it takes to remove them. Okay, so example 1 says, write the chemical equation that represents the third ionization energy of magnesium. So this one here represented the first, this one here represented the second. So we want to write the chemical equation that represents the third ionization energy of magnesium. Well, we've already lost 2, so we have to start with Mg2+, and it's going to become Mg3+, and it's going to lose that electron. And then it says predict. Predict means guess, which means you can't be wrong. Predict the value of the ionization energy for the removal of the third electron. Again, let's kind of follow this pattern here. It was 700, then it was 1400. So I might say that the change in energy on this one might be, I don't know, 2100. Again, I'm just guessing. That's why I like predicting, because you can never be wrong when you're predicting. Okay, 2100, and then again, we'll put those kilojoules per mole in there. Okay, and at this point, we're going to go ahead and stop. Okay, that's a good introduction there to ionization energy, good introduction there to valence electrons, and knowing that valence electrons do behave that atoms with the same number of valence electrons do react in similar, but not exactly the same, ways.